Hi, everyone. Welcome to the Climate Confident Podcast. My name is Tom Raftery, and with me on the show today, I have my special guest, James. James, welcome to the podcast. Would you like to introduce yourself?
Thanks, Tom. My name is James MacNaghten. I'm the Chief Executive of Caldera, and we are a company developing large-scale industrial heat storage.
Okay. Large-scale industrial heat storage. Can you tell me a little bit more about that, James?
I certainly can. So if you look at global energy usage, half of all the energy used in the world today is used to produce heat, and half of that is used for industrial heat. So if we want to decarbonize our world and our society, we have to be able to tackle industrial heating. And within industrial, and it's about a quarter of all energy. It's about 20% of all carbon emissions. And within industrial heat, there's a whole range of temperatures and processes. But you might say, first of all, what do you use industrial heat for? So it's used from everything from, at the very top end, making steel, making cement, to brewing your beer, making a cheese, pasteurizing your milk, sterilizing instruments in hospitals. So there's a very, very big range of applications it can be used for. And in a lot of ways, people tend to sort of talk about industrial heat as one homogeneous sector. It's actually got some very different and distinct, to our view, distinct sort of market segments depending on the temperatures you're interested in.
Okay. Can you, actually, before we get into the detail of that, can you take a step back and talk to me about the origin story of Caldera? Why did you wake up one morning and say to yourself, I think I'll start an industrial heat company and I'll call it Caldera?
Okay, so sort of going back to the dim and distant past, originally I was CEO of a company looking to store electricity by converting it to heat and cold using large thermal stores. This was going back almost 15 years now, when lithium-ion batteries were unbelievably expensive. We were just starting on the journey for solar. Solar was still expensive. Wind was expensive. So it was very much on the journey at that point. And we were looking to develop a process where we took electricity, we converted it to heat and cold, stored it in these big tanks, and then converted it back later. So that sort of started me on the journey. And we were far too early. We were probably a decade earlier than we should have been. While you might say in one sense be nice to be right, we were just far too early. It's even now today, systems like that would only just be starting to be deployed. But I knew quite a lot about heat storage, but I'd always for a long time thought it wasn't particularly valuable. I thought storing electricity was actually much more important. And then we started to do some modeling. We had a sort of project we were interested in where one of the options was you get certain losses that appear as heat, and one of the options was to put the losses into a district heating network. And so we were doing the modeling on the system, and the aim was that you could charge the storage from electricity from wind, and we'd store it, and then any losses you put into the district heating network, and you'll get paid a little bit for them. So the actual system efficiency would be very good. And we used optimizers. So they're optimizers quite good because they run through all the possible solutions, and they can often find solutions that are not obvious. They don't always. You need to sort of bracket them. And we hadn't constrained the optimizer properly. And when we said we can sell heat to the district heating network, it said, don't build any storage at all, just sell the heat. Because actually, even though you're being paid a small amount, it added more value than building lots and lots of capital equipment that doesn't run very often. So that for me was a bit of a shock. I'd always, and the reason it was a shock is actually storing heat is much, much easier than storing pretty much anything else. Your hot water tank in your house, good example of a thermal store. Mm-hmm. And as I said, if you're of a certain age, you'll remember night storage heaters where you used to take an off-peak rate overnight. You'd heat up some very dense bricks inside a poorly insulated container. Yeah. You wake up in the morning sweating, and hopefully by evening there'd still be some heat left to give you some heat in the house. But these are sort of easy examples to understand. But storing heat is actually much, much simpler than pretty much storing electricity, anything else. And so the sort of realization from this was actually storing heat has got a real place to play. And then when you take a step back and look at the best places to go for storing heat, you sort of go, well, if you store heat and deliver it for under 100 degrees Celsius, but you're always going to be competing with heat pumps.
Right.
So So to me, that's never been that's always the risk is at the top end of the temperature range, maybe 80, 90, 100, we compete well, but if somebody wants heat at 30 or 40 degrees Celsius, you'd always use a heat pump. Well, I would tell you always to use a heat pump.
Sure.
So between about 100 and 200, heat pumps now start to run into trouble. Very hard for them to work from ambient. It's actually quite an easy temperature range for us to deliver. So there's a very, very big sector of the sort of heat usage. It's about a fifth of all industrial heat is used in this 100 to 200 Celsius range, and it's normally used as steam. And you probably won't notice it, but lots of hospitals have steam networks, factories do, and they're these sort of big insulated pipes that run around the site, and they basically use the steam to move heat everywhere around the site. And sort of to take a step back, so the realization came that heat storage was important and actually decarbonising heat was important. The breakthrough happened about 5.5 years ago when we worked out how to store. We worked out this thermal storage material, which I'm happy to explain a little bit more about, which we make from recycled aluminium and rock. And it's an amazing material. It's just so easy to use. It's really easy to make into different sized units. So we developed this material, and on the back of it, we're like, this is the business. Because, having built high temperature heat stores before and done it, there were lots of issues, and this sort of seemed to solve all of them. So we pretty much pivoted business overnight to focusing on the aluminium and rock material, and we've been there ever since. We built some domestic units you may know about. So we originally started going smaller into homes for fairly good reasons to do with the price of off-peak electricity. We decided that was not a good place to stay, and we've really moved the business onto industrial. But if you wanted to ask about it, it's basically once we had the material, we're like, this is something we can build a business around.
Okay. And talk to me about the rock and the recycled aluminium, because how did you happen upon that, and why is it, or how is it such a good store of heat?
Okay, so when you have solid materials, if you want to go, the issue is normally how do you get the heat in and how do you get the heat out?
Sure.
So if you have a lot of people want to have piles of gravel or maybe sand where you can blow hot air through them and blow it back the other way to get the heat out, but you need a mechanism of getting the heat in and the heat out. When you have and what the aluminium does, the aluminium is really, really conductive. So it's 100 times more conductive than rock. And what we do is we take a container of rocks, we heat them up, so they're now hot, and we then buy the lowest grade scrap aluminium we can find, and we melt it and we pour it over the rocks, and it runs down between all the holes and it sets and it holds everything together. And I mean, the analogy I often use is if you cut it in half, it looks like a Rocky Road cookie with the rocks in the middle and the aluminium running around everything. And because the aluminium is so conductive, I can put heat in pretty much anywhere in that block, and it will transmit it all over the block really, really quickly and without getting too hot. If you try and generally the cheapest things, and we add the rocks because they're just a low-cost filler. So they have the same density, same heat capacity as the aluminium, but they're much, much cheaper. So you end up with this block of material that on average has the same conductivity as a block of steel. For every kilogram, it stores twice as much heat. It's easy to make, which a big block of steel isn't. And particularly the aluminium, one of the key features is the aluminium is very ductile in the temperature range we use it in. So if I took a large block of steel and I aggressively heated a couple of small bits, the block of steel would probably shatter.
Wow.
It would probably tear itself apart with thermal stresses. Very, very, very high loads you can induce in materials when you heat one bit and you don't spread the heat evenly. So the aluminium is both very conductive, so it moves the heat around. We don't have a completely homogeneous structure, so there's always little gaps, so everything can move. And so the aluminium is really, really important to actually managing how you get heat in and out quickly. So if we didn't have the conductivity, you then end up not being able to put the heat in quickly. So, there are lots of, if I had a lump of concrete, if I tried to heat that, we put electric elements into our blocks and they work really well. If I did the same thing with a lump of concrete, the elements would burn out in seconds.
Right.
Because locally, it would be like you're insulating them, so they'd be over 1,000 degrees Celsius, and they would die very quickly. So by putting them in something that's very, very conductive, everything works really, really well.
Okay, and is it just that you connect both ends of the container full of aluminium and rocks to electrodes and you get resistive heating? Is that how the heat is generated?
We put resistors in the block, so that's how we generate the heat. And then when you want to take the heat out, we embed a steel coil in the block, and we squirt a small amount of water in, and it then turns to steam, and we take the steam out, and we take the heat out of that. And basically, the more heat we want out, the more water we inject.
Okay. And these are kind of barrel-shaped pods full of aluminium and rocks. How much heat or energy can you store in them, and where is that energy coming from?
So the latest versions, which are about 4.5 tons each, they store 200 kilowatt hours. They're 1.2 meters wide, and they're about 2.5 meters high. So that gives you a sort of nice feel for the size of them. And you put them in banks, as you said. So if you wanted 4 megawatt hours, you will put 20 together. So that's what they are. So can you reply me the second question?
Yeah, where's the energy coming from?
Oh, so the energy coming from. So in the longer run, there are two places the energy can come from. It's electrical energy. We don't do heat recovery. So we look to take surplus renewable generation or on-site renewable generation. So there are two. In the near term, we're very, very clear. The best business model we see is where you build a large solar farm alongside the factory. It doesn't have to be, it could be half a mile away, a kilometre away, and you take what's called a private wire, you feed it into the factory's network behind the meter, so the grid doesn't see this. You don't have to pay any of the grid charges, and effectively we provide the factory with both, and this is an important point, it's both electricity and heat. So this works for factories, like a food producer. You might use 1 megawatt of electricity and 5 megawatts of heat. And what you can do is build actually a very large solar array to supply them with both electricity as heat. And we're also able to store heat to carry them through the night, for example, if they wanted to run 24 hours a day. So that's the business case for that works. This is the weird thing. The business case for that works in the UK, which is about the last place it should work because we're not very sunny country. So if you go sunnier countries, it gets better. And the reason is that you're avoiding all of the grid charges and all of the, you don't have to upgrade, there's no export, you don't have to upgrade the grid. And I think that the bottom line is solar PV electricity is now so cheap, at utility scale, it's cheaper than most companies are paying for gas. So they don't care if they displace gas with their own electricity. It's a lower cost. And you put this system in and you displace electricity and gas, and then after maybe 5-6 years you've paid for it, they've now got 30-40% of their energy free for another 20 years. So it's a really, really good way to decarbonize, I would say, large quantities of energy rapidly, because you don't have to upgrade the grid and you can literally go in and tackle it overnight. So that's where we see in the short term. In the longer term, what we're expecting is lots of renewables on the grid, and you're also able to buy, at night when it's windy, you'll also be able to buy electricity from the grid at a low price and also charge. So we sort of say in the near term, it's behind the meter solar combined with our system. In the longer term, it's anything. It's behind the meter, it's from the meter. But the bit that we've still missed today is the market structure, because even when the wholesale price of electricity, which is what the people that own the power stations, the generators, the wind turbines get paid, when that's zero, as a customer, you would probably still have to pay 8 or 9 or 10p for that electricity. And there's a whole lot of charges that have been added onto it that mean, and the problem with charging someone 10p when they can buy gas at, let's say, 7p a kilowatt hour, is they'll stay on gas. So we end up with this very perverse situation where we pay people to turn wind farms off when there are plenty of people that might buy the electricity, because the market structure, and this is in the UK, doesn't incentivize people to try and switch to using it.
Sure. In terms of space, how much space would be required for a as you said, a factory that uses 1 megawatt of power and 5 megawatt hours of heat, just roughly in terms of solar and in terms of the storage space?
So for that sort of system, you'd probably want somewhere between 7 and 12 megawatts of solar. In terms of land usage, depending on how you do the solar, and there is both low density and high density arrays. We're a big fan of high density, but you're probably talking in that scenario anywhere from 10. If you go for high density racking, you might get it into 10 acres. If you go for low density, you might want 30 or 40 acres. So you're going to need a field, you're going to need land available. It's almost certainly too big for the factory roof. We very rarely see a factory roof that can take more than a megawatt.
Okay.
So that would be so you will want access to a friendly farmer from whom land might be available. Second question is how much storage. It depends on how much you want to decarbonize. So what we see in the short term is you would probably be looking for less than 10 megawatt hours of storage. We don't, at current pricing, you're unlikely to go and put in what you would need for overnight, which would be 60 megawatt hours. You could do it, but the payback is longer. So we have a sort of very clear view, which is you need some storage when you do the modelling, but you don't need a huge amount. But it's a sort of a question of how much do you want to decarbonise. Pretty much as in all these things, the more you want to do, the longer the payback. So the first bit always gives you the best payback, but it doesn't have much impact. So there's always a question when you're talking to people, which is, it's not so much what's your hurdle rate, what's your return on investment for your business, what sort of payback do we need, and we size the system to what the customer wants to invest in that respect. And it's a sort of tricky one because we could probably get them to 80 or 90%, but it would be a very, very long payback. And I'm talking very UK specific.
Sure.
If we were in somewhere like the south of Spain, the economics are much better because the solar produces much more energy in the winter period and even a bit more in the summer, but you don't get this seasonality. So in somewhere like Spain, I might have a very different answer where actually we could go and put 40 or 50 or 60 megawatt hours in on day one because we can cycle it every single day. If I put the same system in the UK, I can pretty much guarantee you the thermal storage wouldn't do anything for the winter 6 months at this moment.
Right.
So to me, solar gets you probably, let's say, 30 to 50% of the way there maximum in the UK. It can get you further if it's a sunnier country. And for the UK, we really need access to grid electricity. So I think you would build it out further when you can now buy offshore wind at night and you can actually bring it in. So solar is very, very challenging in the UK because it generates almost the majority of the electricity in June and July, the biggest of months, and almost nothing in December and January. So whenever I model it, you can never, the amount in December and January is tiny.
Sure. But to your point, you can pull in grid electricity at that point and heat the
Yes.
Caldera system that way.
Exactly. So we're sort of like, let's tackle the bit that we can do rapidly, which is the summer heat load and the summer electric load, and we will then build the system out when the grid is there and the tariffs are there. Now, if it wasn't UK, if it's somewhere sunnier, we might go the whole way in a single hit.
Okay. And what are you typically displacing? Is it gas?
Gas. Always gas. Yes, it is. I think we have not yet seen, there might be a little bit of LPG. There is meant to be a bit of oil, but they generally tend to be more rural and smaller. Pretty much all the big factories we go to run on natural gas, and they'll have 3 or 4 big boilers that tower over you that generate steam, and you'll probably have one or two of them running, one of them on standby, and one of them just in case they need to strip it down for maintenance. They've always, and it's really important. These businesses cannot afford to not have heat. From a production point of view, they always want to run with extra capacity. So, we would not say to any of them, we say to all of them, keep your gas boiler. We'll just take a huge chunk out of your energy bill, but you still have your gas boiler there if it's not sunny for a week, if you need to, for whatever redundancy. Because when you're running these processes, if the steam goes off and the heat goes off, things might set in molds. They might, suddenly you have to strip machines down. It's a bit of a disaster. So we often, when we go in, you tend to find they run more machines and they have a lot of redundancy because it's so expensive if something goes wrong.
Okay. And I mean, you mentioned maintenance there. What are the kind of safety and maintenance implications of your system versus a gas boiler?
So we expect ours to be much lower. Gas boilers have certain risks associated with them, especially steam generators. You've got a combination of high temperatures from the flame and high pressures from the steam and lots of what is effectively superheated water. So the water is probably about 180 degrees Celsius, and it sort of boils at that temperature because it's kept at sort of 10 times normal pressure. So our system tends to use very small amounts of water, so it's inherently much safer because most of the energy is not stored in the water, it's actually stored in metal, it's non-combustible inside a vacuum. So our expectation is long-term maintenance is much less than a boiler. But to be honest, boiler maintenance is not a very big part of it. Almost all the running cost is fuel. So I think that's probably the key point to make is the operational cost is dominated by your fuel cost. Even if there's slightly more operational cost on our system or less, it's completely blown away by how much you pay for your energy.
Okay. And in terms of the potential climate impact of this technology, can you kind of quantify how much that would be, how much carbon emission reductions we're looking at?
So if we can help decarbonize the space we're interested, which is 100 to 200, that's 4% of global carbon emissions. So I think it's highly unlikely we'll do all of it, but if we can help bring that sector down to zero, we've knocked 4% off. And I give it, the better analogy I sometimes use is all the cars in the road in the world are 10%. So it's a bit like if we can do this, we can remove 40% of all cars from the road.
Okay, cool. And what's your kind of vision for the future? Where do you see Caldera in the next 5 to 10 years? And, what kind of obstacles are there to stop you getting to that widespread adoption?
So I see us growing to be a much larger company. We want to have offices in Europe and the USA. Those to us are the two sort of key markets. In Europe, you've got relatively high gas prices, and we think they will stay high now because we don't see people returning to being dependent on Russian pipeline gas. So sunnier parts of Europe we think could be very, very good. United States has got the Inflation Reduction Act, which pays for a massive proportion of the capital of both the solar and our thermal storage. So again, we see that offsetting the fact that the United States has much cheaper gas. So it's almost like if it wasn't for the Inflation Reduction Act, actually the United States would be a very difficult market because gas is quite expensive. The one place it's not that cheap is California. So that would be, even within that, I think we'd still find California interesting. So those are the markets we're looking to go to. We're looking to grow the company to, in that period, about the next 7 years, to about 400 people. We're at 20 today. And we want to be installing, megawatt hours of systems. We want solar developers to be calling us up saying, we fitted a megawatt to this factory, but now we've realized with your system we can fit 10 megawatts. Will you supply us with the equipment? And we'll be going, yes, we'll let you go and arrange all the solar, the permitting, the planning. And the key point, I think, that if you said what would hold it up, it's really how quickly can you deploy solar. We think our system has a sort of, because you don't need to export, you don't need to change your grid connection, we think it's probably planning related, but actually can we deploy, is there a field nearby, can you get the consents? These processes realistically are going to take 6 to 18 months. So we think there's a relatively long medium-term lead time on a project, but those are the sort of things that would slow us down or speed us up. If someone comes to me, to give you an idea of where you could go scale-wise, alumina refining, I know this because I've done the numbers, you would want to put in over a gigawatt of solar.
Wow.
And something like 2,300 megawatt hours of thermal storage and some electrical storage as well. So that would be, and there are 80 alumina refineries in the world.
Right.
and they all use basically 80% of their energy usage is steam.
Oh. Wow.
So there's anything from the small, putting a few units in, to actually a really big projects.
Nice. So are they in the same kind of 100 to 200? They must be higher. What's the melting point of aluminium?
No, it's not. They use it's the processing of the alumina. So what they're trying to do is they're trying to separate the alumina out from the other ores. They make it into a sort of a liquor. They add various chemicals to it, and normally that's between 200 and 300 Celsius.
Right.
We can do it, and for that sort of project, we would go to the higher temperature. And actually, it's relatively, if it's a big project, that's not an issue for us. It just tends to be more of an issue on the smaller side. So you basically want heat in the sort of 200 to 300 C range.
Wow. Okay. Talk to me a little bit as well about your funding, because I know you've gone through a couple of funding rounds, and how are you being funded, and how is that going?
So thank you for asking, because we went out and we fundraised a couple of times in the past, but the last time we raised around $1.5 million on a crowdfunding website called Crowdcube. This was in 2021. We're back out there on Crowdcube again. So I have to say there are some risk warnings associated. So if you assume there are risks associated with investing in companies, at our stage on Crowdcube, then I've done my bit for the compliance side. But we are there if you want to join us. We've got 1,300 investors. We're looking to raise a similar sum to last time, and I love the fact that we've got so many investors. A lot of them might know. We can have conversations. They're interested in this space, and you also get lead. People say, I get emails saying, I've got a factory. We use a bit of heat. It's got a big roof. Do you want to come and talk to us? So to me, it's it's both a sort of source of funding, but it's also a source of support, contacts, introductions.
Okay, and talk to me a bit about the offering on Crowdcube. How much can I invest? What's the minimum? What's the maximum? And what do I get for that?
The minimum is £10. I'm pretty sure there isn't a maximum. Although if you invest over, I think if you invest over 20,000, we hold you have your shares held directly in the company. If you're £10, it's held through the Crowdcube structure. So, but in either case, if you're over 20,000, I'll be on the phone to you going, let's have a conversation. So I think, and the most, I think it's rare that people go into the hundreds of thousands, I would say.
Okay.
But that's just from experience. But we're likely to go live. I think when this comes out, we'll be just about going live on Crowdcube for people to start investing properly. At the moment, you can just express interest.
Okay. Cool. And are you kind of set in stone now, pardon the pun, in terms of your technology, or do you see more technological advances in the coming years which will, I don't know, make your product cheaper, make it more energy dense, or
Yeah, all of that. There is all of the key technology bits have been solved, but when you manufacture stuff, you have learning curves. In fact, I think it's almost an achievement for you not to have cost reductions as you improve your manufacturing. I mean, it's natural because everybody goes, you're doing it this way, and they go, well, why don't we do it this way? So why do I need this part? So I would completely expect energy density to creep up. I expect cost to go down. I expect bits to be removed. I expect reliability to increase. All of these things are just natural, but we're really comfortable that the core technology works. And that's on what we're basically going forward from that base.
Okay. A bit of a left field question for you. A lot of industrial things, for want of a better word, come in like 40-foot containers. Is that something you're thinking of working towards, containerizing your batteries? They're not batteries, but they are batteries in 40-foot containers?
No, we want them to be modular and transportable. Mm-hmm. We put vacuum. So one of the points we have both the material. We also put vacuum insulation around ours. So for the reason we think it's much cheaper and it's much more compact, and we found it really easy. It's worked really, really well. The sort of vacuum insulation we use doesn't go into squares. It wants to be circular. Sure. So there is a very good reason these are sort of cylindrical in shape from a structural point of view. So. And what we've looked at is if you put them inside a container, you actually make your knife really difficult from a servicing point of view, and you actually add cost. So while they might be transportable in a container, we're not going to leave them in the container.
Okay, that makes sense. That makes sense. Great. James, we're coming towards the end of the podcast now. Is there any question I haven't asked that you wish I had, or any aspect of this we haven't touched on that you think it's important for people to be aware of?
Probably just the sort of one that I always think is quite useful for people is to understand. So we talked a bit earlier, but when you look at industrial heat, there are really, just to say, people ask why don't you go hotter? So there are two higher temperature bands that are interesting. One's at 900 and one's at 1500. 1500 is steel making, 900 is cement, and both of those temperature ranges are technically very challenging to store heat at and then deliver it at. So we're really, so there's sort of, just to say, there's a really clear reason. So we basically picked this range, which is above heat pumps, but easy to deliver still, and it's just a very big chunk of the market. But we aren't trying to go miles hotter, so for the 900, 1500, because actually they're very, very hard to do technically.
Okay, fair enough. Cool, great.
And it's the one area, steel making is the one area I think hydrogen could be very useful.
Fair, yeah. No, that's true. Cool. James, that's been fascinating. If people would like to know more about yourself or any of the things we discussed on the podcast today, where would you have me direct them?
So I'd have you direct them to our website. It's Caldera, so www.caldera.co.uk. And if you're interested in Crowdcube, there is a link on the front page of our website, or you can go straight to Crowdcube and you could register interest there. But Tom, thank you very, very much for the chance to be on the show today and also to tell everyone a bit about what we're doing.
Oh, thank you, James. Thanks a million for coming on the show today. It was fascinating.
Thank you.